Hello, we're doing checkpoint 5.5. They want us to find the volume of the solid bounded above by the graph. This graph f of xy is equal to xy sine x squared y, and then below the xy, below by the xy plane, and then the rectangular region is 0, 1, 0, pi. Alright, so we want to set up this integral. We can integrate at this point because the region is a rectangular region. We'll have constant limits, and when we have constant limits, it doesn't quite matter how we integrate this. It doesn't matter how we integrate this, which order we integrate. So we have xy sine x squared times y, and if we integrate with respect to y first, and then with respect to x, then our y limits are going to go from 0 to pi, and our x limits are going to go from 0 to 1. Okay, now if we now look at this, focus on this integral, and we integrate with respect to y, which means the x values are constants, we'll have a y on the outside and then sine of y on the inside. And then I'm realizing, oh, we have to use integration by parts. So we'll make a note saying we need integration by parts. And unless we really have to do it, I'd rather not. And so with no consequences at all, we can switch the order of integration. And I want to be careful to say that you can do this because you have constant limits. When we have a more general region that's not a rectangular region, then the switching order will take a little bit more analysis. So we'll switch the order for this case. We're going to go from we'll say xy sine x squared y, and this time we'll integrate with respect to x, and our x values are going to go from 0 to 1, and then we'll integrate with respect to y from 0 to pi. Okay, now as we do that, we'll work on the inside first, which does not require integration by parts because x is x squared inside, and you would do u substitution that would cancel with the x on the outside. And so we'll do that. U sub u will equal to the inside here, x squared y, and we're going to find the differential with respect to x, so 2xy dy. And not only do we get the xy, or not only do we get to get rid of the x, but we are also replacing the y there, and then the 2 can go as a denominator, so we get y is equal to du over 2, and the dx, or the xy, would cancel. Okay, so continuing to work on the inside integral, we're going to get sine of u, and there's a 1/2 sitting out there, du. Okay. The limits are still going to be x limits, so I can label it as x goes from 0 to 1, and the antiderivative sign is negative cosine, so this is going to be negative 1/2 cosine of u, and let's put the u back, which is x squared y, integrating from x going from 0 to 1. If we put 1 in there, we're going to get 1 in for x, we're going to get cosine of y, and if we put 0, cosine of 0 is 1, so let's just put that there. Okay, and this is going to be in the inside of your integral. I think we have we missed the negative sign over here because this should be negative 1/2, and then the the integration says it's going to be this expression minus the second expression, which is a negative a half. All right, now that we got that fixed up, we are on the outer integral, and the outer integral is going to go from 0 to pi of, we just computed all this stuff and got to this, so it's negative 1/2 cosine of y plus 1/2, and this time we're going to integrate with respect to y going from 0 to pi. Okay, we integrate with respect to y. The antiderivative cosine is positive sine, but there's a negative 1/2 here. This becomes sine y plus 1/2 y. And we're going to integrate this from 0 to pi, or evaluate from 0 to pi. And we don't have any other variables, so I know it's going to be a y that's going to go in there. We put pi in for sine. Sine of pi is 0 plus 1/2 pi minus, and then we put 0 in there. Sine of 0 is 0 again, plus 0. So all we have left is pi over 2. Okay. All right, so again, we took advantage of the fact that these are constant limits and we can just switch the order of integration when we didn't find a convenient finding the antiderivative of the first part in this particular order. So instead of going dy dx, we went dx dy, and that required a simple use substitution instead of a more complicated integration by parts. Okay, I hope that helps.